Okay, we are now in chapter 17, the last chapter of the term, Physics of Hearing. In the last chapter, we learned about oscillations and how oscillations can make vibrations and simple harmonic motions, and we also learned about a little bit about waves as well, and resonances and everything else. In hearing, we're going to focus specifically on sound waves and how they behave. We got 7 sections to cover really quick. And let's get started here. There we go. So, sound waves, of course, are a compression wave. And here is an example of a compression wave. You have a string, like on an instrument like a violin or a guitar or something, and when you pluck it or you use a bow on it, it vibrates back and forth and back and forth. And when it's pushing forward into air, it creates a compression of the air, and when it's moving away from some air, it creates what we call a rarefaction, essentially the opposite of a compression of air. High pressure on one side, low pressure on the other side, but that air has to come from somewhere. It comes from around. When you create a pressure in air, it's like you're squeezing air together, but that air has to come from the area around it, and so it creates these low pressure regions, and then those low pressure regions create high pressure regions around them, and so on and so forth, and you get a wave that starts moving outward. And sound has, when there's a source for sound, it creates a wave that moves outward from that source in a spherical way, in every direction in three-dimensional space. And you could map out the pressure on a distance scale. So this y-axis is the pressure, this axis is the distance away from the source, and you'd have a high pressure, low pressure kind of situation going on, high pressure, low pressure. And as that high pressure, low pressure wave propagates outward, eventually it can reach your ear, and your ear has the mechanisms inside it to turn that pressure wave into impulses that go into your brain. And we'll talk about that a little bit later, how that works. Let's see if I can get this thing to work here real quick. Had a hard time earlier making it work, but maybe we'll get lucky. No, apparently not. Well, we'll have to leave that for now. But anyway, point being, let's move on. So sound waves have frequencies, and they have a speed as well, and they have wavelengths, and it turns out the frequency, the speed, and the wavelength are all related by this equation. You multiply the frequency by the wavelength, you're going to get meters per second, which is the speed of the wave as the wave moves outward away from the source. We call it the wave speed or the wave velocity, and it's frequency times wavelength. You can also take the wavelength and divide by the period and get the velocity of the wave. But it turns out that the difference with sound waves is that they have all these different speeds. Well, it's not really different from other waves. Many waves have different speeds, but the speed of sound depends on what kind of material it is. In air, it's about 331 meters per second as long as the air is at 0 degrees Celsius and it's at normal kind of pressure, like 1 atmosphere at sea level. The higher you go up in the atmosphere, the speed of sound gets higher and higher and higher. And carbon dioxide, a little bit lower speed. Oxygen, about the same as air. Helium, it's actually a much higher speed. Hydrogen, higher still. And you can see that ethanol, mercury, water, seawater, human tissue are all much, much higher than air. So the sound actually travels very quickly through solids and through liquids than it does through gases for the most part. You can see here that hydrogen actually has a very high speed. And the reason being is because hydrogen is actually just a very, very small atom. And so if hydrogen is accelerated by a pressure wave, it accelerates very quickly, and so it can propagate that sound. Sound waves are literally the movement of atoms in material. And so you can see here some solids have, like steel, it's 59, 60 meters per second. It moves really fast through steel. Sound does. So what happens if we're not at that 0 degrees Celsius and we're not what's going to happen is the speed of the sound is going to change, and in fact it will increase as you get hotter and it will decrease as you get cooler. The reason for that again is that if it's hot, the atoms or the molecules in the material are already moving very fast, and so they can transmit that signal faster. And you can use this equation where T is the temperature of the gas in question or whatever it is. It doesn't have to be a gas, but it's the temperature in Kelvin. So, and in this particular one, it's since it's starting with 331 meters per second. This is for the speed of sound in air, but that beginning number will change for different gases, and in fact, this formula changes slightly. And then you can get the RMS speed of the particles in the gas. That's what I'm trying to say. So the average speed, which is the root mean squared, the average speed of the particles in any particular gas, is 3 times k times t over m, and that has a lot to do with how the speed of sound changes as temperature changes. But again, still the speed of the wave is just the frequency times the wavelength, and so those things must change also in different materials if the wave velocity is going to change. So a lot of things change with waves as they go from material to material, which turns out to be a very important thing. But from this equation, if you have the same velocity because you're in the same medium for a wave, if you have a large f, you're always going to have a small wavelength. A large frequency means small wavelength. If you're going to have a small frequency, it's going to be a long wavelength for the same, if you're in the same medium. And what that translates to is that low sounds, long wavelengths, in other words, have small frequencies. High sounds have high frequencies and short wavelengths. And here they just calculate that using the equations we've been given so far. They calculate the velocity of a wave using the temperature equation, and they plug that into this equation up here to calculate the wavelength. Once they've calculated the wavelength, they can tell you the maximum and the minimum wavelengths that we hear at for different frequencies. 20 hertz for the longest wavelength, or the lowest tone that we hear. Turns out for 20,000 hertz, we get 1.7 centimeters for the smallest wavelength that we can hear. Now, how do we measure sound? Our ears actually hear a huge range of sound intensities. Intensity is defined as the power. Remember, power is energy per time. And so intensity is the power divided by the area, or the energy divided by time divided by area. It's essentially how much energy is going into a certain area over time. And that's what intensity means. In the end, it has something to do with pressure and density as well, and the velocity of the wave, and they show us that equation here, which comes from thermodynamics and a bit of mechanics, but statistical mechanics in particular. But in the end, it comes down to a change in pressure as these pressure waves go by, but it's also dependent on the density of the material and the velocity of the wave. And so here we can see this little illustration. This bird here has a very, very small squeak, and you can see on this graph here, we're graphing the pressure wave versus distance. So as the pressure wave propagates through space, in other words, we got this very small pressure wave, and it's very low intensity, and that is related to the amplitude here, or the distance between the center line and the peaks and the troughs of the wave. But a high intensity wave has a much higher amplitude, so amplitude and intensity are related. But because we hear with such a wide range of intensities, we actually measure it and talk about it in a very different way. So the lowest intensity sound that we can hear is 1 times 10 to the minus 12 watts per meter squared. So that's a tiny, tiny amount. That's less than a trillionth of intensity, essentially, less than a trillion watts trillionth of a watt per meter squared. And we can hear things at that. We have to be very quiet and really be listening, but we can do that. A rustle of leaves is 10 times greater than that. It's 1 times 10 to the minus 11. A whisper at 1 meter distance, somebody's trying to whisper at you and they're sitting next to you or 2 chairs down from you or something like that. It's 1 times 10 to the minus 10. And you can see that we can hear things all the way up to things that are 1 times 10 to the 4 or 10,000 watts per meter squared, which is where our eardrums essentially will break and rip. But we have this huge range that we can hear in. And we don't want to measure, we don't want to have numbers that we have to write down for intensity 1 times 10 to the minus 5, 3.6 times 10 to the 2 or whatever else. It's just too many numbers to write down. So what we do is we just ignore this intensity number and we just look at the number in the exponent, this negative 12 for example. This is the lowest intensity thing that we can hear, the quietest thing that we can hear. So what we do is we created a scale that we call the decibel scale, and it uses a 0 at the lowest level. So the lowest level of hearing is 0, and that's 10 to the minus 12. 10 times bigger than that, 10 times louder you could think of it, or 10 times more intense than that, we call 10 decibels, and that's 10 to the minus 11. 10 decibels is about what the rustle of leaves is. 10 times more than that, we just add 10 more. So it's 20 decibels for 10 times louder than that, which is a whisper. Then we add 10 more for 10 times louder than that, which is 30 decibels for a quiet home. And you keep going all the way up to the loudest thing we can hear without hurting ourselves, which is 140 decibels, which is like a jet airplane when you're standing near it. And that can be really painful and it can cause damage. But this sound intensity level that we use, the decibel system, is confusing to people because if you're listening to something that's 30 decibels, like a quiet household, and then you listen to something that's 60 decibels, 60 decibels is not twice as loud as 30 decibels. You would think it is because 60 is twice as big as 30. But every time you go up 10 decibels, so if you go from 30 to 40, that's 10 times greater. So 30 to 60 is certainly not 2 times greater. 30 to 60, you have to go from 30 to 40, which is 10 times greater. Then 40 to 50, which is 10 more times greater, so it's 100 times greater. And then 50 to 60, which is 10 more times greater, which is 1,000 times greater. So 30 decibels, the difference between 30 decibels and 60 decibels is 1,000 times louder. So a quiet home with nothing going on in it, just a little bit of background noise, is 1,000 times quieter than a normal conversation you might be having with somebody. This decibel scale is based on an exponent or a logarithmic equation, which is based on an exponential equation. And this is how the equation goes. The decibels, which is this beta on the left side of the equation, is equal to 10 times the log base 10 of this ratio of the intensity of the sound that you're interested in divided by I0, which is the intensity of the lowest thing you can listen to, which is the threshold of hearing, 10 to the minus 12. So you take whatever intensity sound you have, divide it by 10 to the minus 12, take the log base 10 of it, and then multiply it by 10 and you'll get how many decibels it is. It's a bit confusing, it's a bit convoluted, but it works very well. And some things that you definitely want to remember, especially for the homework, is that if you double the sound, so if I2 over I1 is equal to twice, so you have twice as much intensity in sound, it only changes the dB or the decibels by 3. So if you have 12 decibels of sound and then you hear something that's twice as loud as that, it will just add 3 dB, so it won't be 12 decibels, it'll be 15 decibels. 15 decibels is twice as loud as 12 decibels. And if you have 5 times as much intensity, then it increases by 7 decibels. So an airplane that is 5 times louder than your stereo, and your stereo is at 100 decibels, then the airplane going over would only be at 107 decibels, because that's 5 times louder. And then 10 decibels, of course, means that it's 10 times greater, like we said before. So in this problem, 17.2, we've got this, we're going to calculate the sound intensity level in decibels, so for a sound wave traveling in air at 0 degrees and having this pressure amplitude that they've given us. So we're going to use the equation that uses the pressure, and we need the rho here. This is not a P, this is a rho, which is the density of air, 1.29 kilograms per meters cubed. And then you have to also plug in the velocity of the wave in that air. So 331 meters per second. And then we can go ahead and we can calculate I from that. We can calculate the intensity. Once we've got the intensity, which they have right here, Then we can enter that into the equation for the decibels. We divide that 5.04 times 10 to the minus 4, divide it by 10 to the minus 12. We take the log base 10 of that, we multiply by 10, and we get 87 decibels for that sound. Now, if you wanted to hear something twice as loud as 87 decibels, you would increase it by twice as loud as 3 decibels. So you would increase it by 3, and you would go from 87 up to 90 decibels for something twice as loud as that. And here they do that. They talk about I2 over I1 is twice as big, and then your beta 2 minus your beta 1 is 3 decibels. There we go. Okay, so now we have what we call the Doppler effect. Let's see if I can bring up some interesting things for the Doppler effect. Okay, I want to find one that actually plays the sound. I'm trying to remember which one plays the sound in the Doppler effect. I think I can't remember. Let's try this one. Let's see if these work for us. Okay, so here is the Doppler effect. Where is the Doppler effect? Here we go. We're getting close here. There it is. Okay, apparently my security preferences aren't allowing me to do this. Let's fix it here really quick. Security preferences. Okay, let's go back here and open this up. Okay, open. See if I can get this to go. It's not letting me go. It's because I don't have the Java runtime environment saying this. Here we go. See if I can get this working really quick. I'm going to pause my thing for a moment. Maybe I'm going to pause it. I don't know if I can pause it. That's okay. We'll just download this really quick and make it work, hopefully. Ugh. Hopefully it won't take too long for it to run. What I'm downloading is called the Java Runtime Environment, and it's helps to run simulations on computers that are realistic. So a lot of science experiments on computers are run in Java. Let's see if we can get this to work here. Alright, let's try this again. Good night. What is going on? Why am I in the App Store? I don't want to be in the App Store. There we go. Well, this is not being very helpful for me. Well, it's not working for me. I don't know why. Let's look for a different one, I suppose. Online Doppler demo. See if I can find one here. Not what I'm looking for. Try this one. It's promising. Okay. I don't know why this isn't working. It's not working though. Oh, this doesn't help either because it's not the right Doppler shift that I want to talk about right now. Let's try another one. Okay, let's see if we can figure something out here. This is not quite right either. Here's a better one. So here is a sound source, and we can't hear it, but the red lines coming out, the red circles coming out from the source here represent the peaks of the sound waves, or the high pressure points of the sound waves. And the source is, of course, the green dot. As the source starts to move to the left, though, what happens is that it catches up to the peaks in front of it. It kind of makes this area in front of it have much shorter distance between the peaks. Well, the distance between the peaks is the wavelength, and that affects the frequency. So the frequency in front of the green dot is higher, and behind the green dot they spread out as the waves move further away and the source moves further away, and so the wavelengths get longer. And the result is a change in the sound, and we've all heard it. As a car goes by on the road, the engine and the tires of the car and the wind going around the car are all making a sound with tone qualities. And as it's coming towards us, we are hearing the sound that's being squished together, higher frequency. And so it sounds higher. And then as it goes past us, we hear the sounds that are being stretched out, so it sounds lower. And we get that as it goes from high, low, right? That is the Doppler effect. And it happens with anything that is emitting a wave and moving. So sound waves are that way. Water waves can be that way if you have a boat moving through the water. The really interesting thing is what happens when you go the same speed as the sound. And when you go the same speed as the sound, you will actually catch up to the waves. And let me show you what that looks like in the book. So when you catch up to the waves, you must have missed it somewhere. Where did it go? Well, let's actually not talk about that. Yeah, let's talk about this first. So these two equations are actually the equations that will help you to calculate how much that sound wave has changed, how much the frequency of the wave has changed. So you have the frequency that is observed. This is the frequency of somebody who is listening to the sound. And then the frequency of the source. So that's the source that's either moving or whatever else. But that's the thing that's making the sound. And then you have the velocity W and the velocity S. The velocity W is the velocity of the wave, so the velocity of the sound. The velocity S is the velocity of the source of the wave, or the source of the sound. So Fs and Vs are the velocity and the frequency and the velocity of the source. And if you use this equation with a plus sign, then you're going to get a frequency that is lower than for the observer than it is for the source. And so the plus sign is when the source is moving away from the observer. The negative sign will give you a frequency that is higher, and that is when the source is moving towards the observer. Now, what happens if the observer is moving? Well, it does change things, believe it or not. If the source is sitting still and the observer is moving, you use this equation here, where the VW plus V observation, this plus or minus thing, is in the top of the equation, and then you have the V velocity of the wave in the bottom. But still, you have frequency of the source and velocity of the wave and velocity of observer and frequency of observer. Right? And you plug them all in here properly. Now in this case, when you add together the two in the top, you're going to get a bigger number up top, frequency for source, and that's when you're approaching. So adding is for approaching this one. When the observer is approaching the when the observer is approaching the source. And then the VW minus V observer is going to give you a smaller frequency or a longer wavelength, and so that's when you are going away from the source of the sound. So the top one, the plus means the sound is going away from you, the minus means it's coming towards you. For the bottom one, the plus means when you're going towards the source, and the negative one means when you're going away from the source. It's kind of opposites for those. And they tell you that in here. But you can calculate the Doppler shift for a train horn, for example. You have a train that's moving along, and you have a person standing next to the train, or standing next to the tracks as the train comes towards them. What is going to be the observed frequency for 150 hertz horn, which is the number you put in for the frequency of the source, and the velocity of sound in the particular air that they're dealing with, it turns out to be, the velocity of the wave turns out to be 340 meters per second, so they put that in there. And then the velocity of the train is 35 meters per second. You put all the numbers in, calculate it, and since they're, so for moving towards, use the minus, for moving away, use the positive, and you get a change in 17 hertz, positive 17 hertz, so the frequency goes up when the train is moving towards them by 17 hertz, but it only goes down by 14 hertz when it's moving away. So it's not the same change on either side, and that's really quite interesting too. And you can actually show that when you're standing right next to the train, or you're standing in the train, that the observed frequency and the frequency of the horn are actually the same. Because in that case, the velocity of the train and the velocity of the observer are the same, and they cancel out, and you get a 1 times the frequency, so it doesn't change at all. Now, what happens when the velocity of the source becomes the same velocity as velocity of the sound? You plug those things into this equation and you get some really interesting results. And this is what happens graphically. You see the sound is moving out away from the source as it's moving to the right, but the source is actually catching up with the sound here on everyone. And you're getting this wall of sound out here as it builds up behind the source. And the faster you go, the tighter that wall gets, and essentially you get this big wall of pressure here. And as you get towards the ground, that wall of, if you're near the ground, that wall of pressure will cause problems on the ground. It can hurt people's ears, it can be really loud, it can even break glass. So that's what we call a sonic boom. You're going at the speed of sound or beyond the speed of sound. You drag behind yourself a big wall of pressure that is the sound all building up on itself. The same thing happens though in other mediums with other waves. So like in water waves, a duck will move as fast or faster than the waves that it makes. And so it creates this V-shaped sonic boom, you could think of it as, but it's more like an aquatic boom. It's what we call the wake. And so speedboats leave a wake, and so do many waterfowl and even fish. They leave wakes because they're going the same speed or faster than the waves that they're making as they swim along. Okay, now sound interference and sound resonance. So if you make a sound by like vibrating this tuning fork here, and then you put it into a tube that has a closed end, what happens is that the sound wave goes out and it bounces off the end of the tube and comes back. But as it bounces and comes back, it actually can build up on itself. It can actually create sound waves that are on top of each other, because the sound that's going down is on top of the wave that's being bounced back. And so you can get some really interesting effects with that. When you have a situation like this, with sound waves in a tube, you have to consider physically, how does the pressure behave in the tube? And so what we're going to do is we're going to look at some very specific types of tubes. This particular type of tube has, let's see if I can, let me see if I can figure out what they've done here. This is a closed-end tube. Yeah. really don't like the way they do this, but I'm going to do it anyway. So this tube essentially is closed off at this end down here, and it's open at this end with a little tiny hole that we put the sound in with. And at the open end, the pressure is going to essentially be zero, or not zero, but it's going to be essentially the same as the pressure outside because it's open to the outside. However, the further you go down to the tube, the more the pressure is either going to be really high or really low as the air in the tube slams up against the wall from the pressure or it gets pulled away from the wall. So you have high pressure here and low pressure here as it goes back and forth between high and low pressure. Well, this does kind of look like a wave, but it only looks like part of a wave. This would be the whole wave. So it's only a quarter of the wave. But that's nice because it takes only a quarter of the length of the wave to make that wave inside this tube. You'll still this quarter of the wave will still have the same effect on the ears as if we had the whole wave present. And so to make really, really low notes, which are really, really long waves, on pipe organs, they actually use a tube that has a cap on the end of it that's closed end, so that you can make really, really long waves with a really, really short tube. However, that's not the only kind of wave that you can make. You can make any kind of wave that starts off with a pressure that is equal, right? It's equal to the outside pressure, so it's right here in the middle, and ends up high. So if we go from the middle pressure up to a high pressure, back to the middle pressure, and then back up to that high pressure at the end again, this still has the high pressure, low pressure thing going on at the end, and it still has the equilibrium pressure on the other side, but we've now fit in 3/4 of a wave, and so that's another tone or another wavelength. It's another sound that we can make with this tube. And then, in fact, you can make even more, many more that look very similar, but they just have more and more of these places where the pressure goes through the equilibrium point. Those places where the pressure goes through the equilibrium point we call the nodes, and then the places where it's high pressure, low pressure we call the antinodes. And so for a closed-end tube, you have the longest wave you can make, which we're going to call the fundamental wave, which is 4 times the length of the tube. So lambda 1, or the fundamental wavelength, is 4 times the length. Fundamental frequency is therefore the velocity of the wave divided by 4 times the length. And then the next wave that we can build, this one where 3/4 of the wave fits into the tube of length L, we're going to call the first overtone. And the next one we call the second overtone, and the third overtone. Sometimes we call the fundamental the first harmonic, and then this one the second harmonic, and third harmonic, and whatever else. But these are all waves that you can create, standing waves inside this tube, and it will resonate, and it will sound big and loud and good. And this is actually how different instruments get their different tone qualities. For example, a trumpet has a very different sound than a clarinet or a piano. And that's because they have different mixtures of these waves that are louder and softer in different instruments because of the shapes of the tubes and how the tubes are designed. Our voice is very similar. It's kind of like a closed-end tube down our throat and an open end up by our mouth. And we can make vibrations deep down, and those vibrations come out through our mouth and after they've resonated and everything else. The interesting thing is that one of the interesting things about this tube problem is we can actually create an equation for the frequencies inside of tubes. And this is the equation that they've just made for us, going through the physics of the situation. The frequency of some n, where n is 1, 2, 3, 4, 1, actually for a closed-end tube it's 1, 3, 5, 7, it has to be an odd number. The frequency for those overtones is equal to that n times the velocity of the wave, or the velocity of air in the tube, divided by 4 times the length of the tube, and n has to be equal to the odd positive integers. So here they just have you calculate. They give you the frequency f, they want you to find the length L, and they're assuming that you can calculate the velocity in the air that you're dealing with, or whatever it is you're dealing with. So the velocity of the wave. You go ahead and do that. Turns out the velocity of the wave in this case is 331 meters per second times 295 over 273, which is 344 meters per second. And you take that and you plug that into your equation with your frequency and solve for the L, and you get this equation. Not a big deal. People who design organs are doing this all the time. There's another kind of pipe that you can use, which is open at both ends. So both ends or the air can move at, and they use or the both ends of the air is essentially at the same pressure, and so you can use any representation you want. In this case, they're using the open end to be these the movement of air here. So this is essentially fitting in right here as a half a wavelength, and so whatever wave you can fit in here, that fundamental frequency is actually, or that fundamental wavelength is actually twice the length of the tube. But the other one was 4 times the length. This is twice the length. But this will give you different overtones, different harmonics. And so it will sound different, have different tone quality. And they have, again, another equation here. It's equals the frequencies equal n times the velocity of the wave over 2 times the length of the tube, where n is equal to 1, 2, 3, 4, and so on and so forth. Not just the odd numbers, but all the positive integers. And every instrument is designed to take advantage of this slightly differently so that you get different sounds. And even different shapes. A guitar is a different shape than a violin in its resonance cavities, which is a different shape than this funky little thing that they're playing wherever they're playing that. And even pipe organs have different shaped pipes just to get different sounds. I'm going to not spend much time on that for a moment. Quality of speech. Here they're talking about kind of the medical measuring of hearing and everything else. I'm going to skip that for a little bit. It's not that hard to read off the charts. But this here shows the actual, it actually shows a diagram for how the ear works, how the inner ear works. So it's essentially a force diagram for the inner ear. You have the pressure, the sound that comes in here down on the bottom of the diagram as pressure 1. It's a pressure, an air pressure that hits your eardrum. And as it hits your eardrum, it applies a force to this bone that is called the hammer, which is connected to or touching the eardrum. So you have the pressure on the eardrum creates a force on the hammer, which creates a torque actually on this place with this thing we call the anvil, which is another bone. And that torque creates a force on the stirrup, which is another bone. So 3 bones, tiny little bones, they're the smallest bones in your body. That final force that's on the stirrup puts a force on what they call the oval window, which is connected and kind of surrounds your nerve. And they'll show you the nerve here. So here's the oval window is down in here. It's kind of like an inner eardrum. But this big thing right here surrounds your nerve, the auditory nerve, and sends those signals to your auditory nerve. And your auditory nerve gets these impulses that are turned essentially into electricity by this pressure that's turned into forces and then turned into another pressure. So that's how it works. It's just forces, pressures, and impulses. And there are 2 kinds of sound that we often hear about. One of them we hear about more than the other that we cannot hear as human beings. One is called infrasound, which is sound waves that are too low for us to hear. The wavelengths are very, very long. Those kind of sounds are often the kinds of sounds that are created in the earth. We feel them as shaking, and we don't hear them so much, but we can feel them as vibrations. That's infrasound. Also, waves. Not waves. Whales and other animals in the ocean can often use infrasound. These very low frequencies that we can't hear. And they also use ultrasound. Ultrasound are frequencies that are higher than our ears can hear. And ultrasound is the kind of sound that we use also to do lots of medical things with. So here we're looking at a baby using ultrasound. Essentially, they send in this very high frequency sound, and it bounces off of different materials differently. So skin bounces the sound a little bit, but bone does it a lot. But ultrasound is not just used for making images, it's also used to break things up in the body, particularly tumors and gallstones things that need to come out of the body but are too big to come out very easily, we break them into smaller pieces so we can take them out better. So tumors in the brain, for example, we don't really want to get into the brain and take chunks out of the brain, especially if they're somewhere in the middle of the brain. So we put in a probe, or we send in a sound wave somehow that is very, very high frequency and will break up that tumor without doing too much damage to the brain, hopefully. And we do the same thing to other things, the gallstones in the bladders of the body and other things like that. So the great thing about that is that it can help us to get rid of bad things in our body without really causing too much other damage. Whereas before, doing surgery on those things can be really dangerous. And surgery in general, cutting open the body, is a very dangerous procedure. So here they show the speed of ultrasound waves as they go through different things. So they go through air, 330 meters per second, just like normal sound, but water, 1500, right? And those different speeds actually determine how the image comes out, or what kind of effect it has on those things in the body. Here we can talk about the intensity reflection coefficient, which will tell you how much sound will reflect off depending on this factor, which we call the acoustic impedance, which is kind of like the resistance of the material to sound. And so if you know the acoustic resistance of the two materials, the material you're going through and the material you're going to bounce off of, then you can actually calculate how much is going to be reflected back using this equation. They do this in this example down here. They have ultrasound that's going through the fat tissue, and it's going to bounce off of, it's going to go from fat to muscle, so it's going to bounce off of muscle tissue. So you look up the Z for the fat and tissue and the muscle tissue up here. So here's the fat 1.34 times 10 to the 6. The muscle is 1.7 times 10 to the 6. You plug those two numbers in in this equation, and you're going to be able to calculate something. Oh, they're actually having you calculate the acoustic impedance of fat tissue, which we already have. But then in part B, we're going to do the reflection coefficient, plug in the acoustic impedance of fat tissue and muscle tissue into this equation, and we get a reflection coefficient of 0.014. And that will tell us essentially how to program a computer so that it can know when sounds come back, if that's fat or muscle or bone or whatever else, and it can create an image. Because the sound that goes in for ultrasound comes back with reflections, and it actually is going to need to be turned into an image by a computer, because it just sends back intensities. So the computer has to do that. And what the computer sees is all these intensities that come back at different frequencies. So you have some frequencies that come back at higher intensities and others come back at lower intensities. And so you can create that, you could map that into an image and make an image of a baby right here. Right? Here they're doing a 3D ultrasound. And 3D ultrasound just has to do with using multiple sounds coming from multiple directions and then letting the computer create a three-dimensional image of that. Also, you can do moving objects using Doppler shift, and you can know how the frequencies change as things move. You can even use ultrasound to calculate the velocity of blood in the veins. You have a speaker that is, you have speakers and microphones that go along, and they're essentially going to listen to the sound of the blood going through your body at different points in your arm, for example. And then they're going to use the Doppler effect to determine how fast things are moving, because it's going to change things. You have this Doppler effect going on. They talk about that in this example. They're using the Doppler effect equation, so it's not the Doppler shift equation. It's not terribly difficult. We've done it before. And that is the last chapter, chapter 17, the physics of hearing. And I, again, will be posting videos on homework problems. If you have any questions on particular homework problems, that would be the best thing to do, is send me a particular question so I can answer your particular question. Otherwise, I'll just go through and try to give you a nice sampling of how problems are done in chapters 16 and 17. And we'll try to get this homework all done sometime early next week, hopefully, and get the grades in and everything kind of hammered out, final stuff hammered out. And we'll talk to you guys later.